Okay. So good morning. So we are now going to have lecture number 26. This is on 5th April 2021. So in the last period, we have just derived our governing equation for pure cornering study in a particular form called the state space form. So that was represented by Q dot equals A into Q plus B into delta F. So where this Q vector 2 by 1 vector is called the state variables, and A matrix is what is called the state matrix, and this B vector is what is called the input vector. Of course, steering angle delta F is what is an input, and this is an input vector B, right? So now what is the advantage here is, let me take this state variable Q is represented by this, what is that is Q times e raised to st, e raised to st, right? Just a minute. That means here I have my state variables V and R. So that would be equal to V R e raised to st. So what is this? Is a trial function, trial solution function. My response is going to be in this exponential form given. Then you see in this, what is S is Laplace constant. So S is Laplace variable, Laplace constant, and you can have this in a complex plane representation, right? So now, if I substitute that in this equation, what would happen is that V R, it's not V by R, V R and since it is Q dot, it is going to be S e raised to st, and this side it is A into V R S e raised to st. So there is no S here, e raised to st, and here you would have B into delta F, right? B into delta F. So, I'm going to now, what is my objective is to get my characteristic polynomial, and then I will get my characteristic equation. I'm going to represent this in this form. So let us have this on this side and take this onto this side. So when I bring this onto this side, this is going to be in this form. What is that? It is going to be Si, since it is matrix and vector involved, Si minus A into e raised to st. That's what is equal to B into delta F. B into delta F, right? B into delta F. Just a minute, 1 minute. I just have some disturbance here, sound. I'll just address that. Okay, sorry. So let's continue now. See this here. This state space form of this representation can be useful for two aspects. One is to do stability analysis. Let us look at that separately, wherein we will make this input is 0, and then we will do perturbation analysis. It's called, or free vibration study. It is called, so that we would be able to talk on its stability. That is one thing. And the second one is to get a characteristic polynomial. So if I have my characteristic polynomial, then I can again talk on what is again that can be reduced for an algebraic form. So representing this governing equation, which are in differential form, to convert that into an algebraic form, I can do that. So here you see this entire term. How do I get? How do I get characteristic polynomial? Why do I want to get a characteristic polynomial? When I say it's polynomial, it is not a differential equation. So if I have my characteristic polynomial, I can represent this equation into this form. So in this case here, it's going to be like that. I will have a C matrix times my X, that's going to be equal to B. So these are the algebraic form equation. So where the C is simply Si minus A. Si minus A. Si minus A. Right? So here, Si minus A, it's not only e raised to st, it is v, sorry, this vector I missed, that's why there is like, so v, right? So this is what is your x, and this is b. This is the Si. So in this form, it could be represented. So if I have this, then how do I get my characteristic polynomial? Is simply by finding this determinant Si minus A. So why do I have to get this determinant Si minus A? If I do this determinant equating to 0, that's going to give me a characteristic polynomial, characteristic equation. So characteristic equation is the one which is going to have quite useful form for stability analysis, where like we have represented industrial gradient you would be able to represent what you call a stability factor there. So let us just find out this characteristic equation now, correct? So characteristic equation to get, I would make this Si minus, I would find this determinant and equating to 0, I would get characteristic equation. Characteristic equation. So what do you mean by, what is the difference between characteristic polynomial and characteristic equation? Characteristic polynomial is the polynomial which is coming out of this determinant Si minus A. When I make that is equal to 0, then it is called a characteristic equation. Characteristic equation. Why do I have to get this? Is because I have now this is into this form, C into X is equal to B form. So I can find out the steady state gains. So this is useful for finding transfer functions, or you can say steady state gains. So what is the difference between transfer function and steady state gain? Transfer function is the ratio of polynomials. Steady state gain is what is going to be substituting S tends to 0 in that. So S tends to 0 is something what is called an initial value theorem or final value theorem. So final value theorem is what I have my response. In that response, at t tends to 0, I would get my steady state. So I require a steady state gain. So as t tends to 0 in Laplace domain equivalence would be equal to S tends to 0. So that is what is the final value theorem that you see in Laplace transform. So anytime you have your differential equation and their solution like this, the response would go to its steady state response as t tends to infinity. There is some settling time where the transient vector, the complementary function would die out, and you will have a steady state response. That is why t has to go to infinity, they said. So that equivalent in S domain is S tends to 0. So if you put in transfer function S tends to 0, whatever that you get is what is called the steady state gain. So that's what I am going to get. So to get that steady state gain, I require now my characteristic equation. So this, let us just first derive this characteristic equation. Then we will go for using this equation. Say let's call this equation is 3, and this equation you see that you can easily apply a rule called Cramer rule. Cramer's rule. So what is that Cramer rule state? It is that every variable in a set of linear algebraic equations. So I get here a set of linear algebraic equations. So C is 2 by 2 and it's 2 by 1 and it's again 2 by 1. So I get a set of linear algebraic equation. So this variable can be expressed as a ratio of two determinants. So one numerator determinant is Si minus, denominator determinant is Si minus A. Numerator determinant would be expressed by replacing in C by this first column. So we will see that how do you apply this Cramer rule to get your steady state gains. Right, so let's first find out what is this characteristic equation. So making polynomial equating to 0 is what is characteristic equation. So for that, let me just find out this determinant. Right, so this determinant is going to be now simple. So I have my A matrix, state matrix already derived in the previous lecture. Right, let us look at that. So what was that we derived? You see here we have our A matrix. Our A matrix. So this is 2 by 2 A matrix. So Si minus A. So S is Laplace variable S. So S 0 0 S is what is 2 by 2 Si. So let us just work out that determinant. I'm sorry. So how do I do that is in this way. So let me work out for Si minus a equals 0 to get characteristic equation. So I would have my determinant now. So S minus the first term what was there in my A matrix. So it is S plus C alpha F plus C alpha R by mu. Right? So that minus goes off. And there it's 0 minus of that. So I will get minus now. So this is going to be minus AC alpha F by plus BC alpha R by mu minus u, and this term is minus AC alpha F plus BC alpha R by IZZ u, and here again S minus of minus term, so it's become S plus A square C alpha F plus B squared C alpha R by IZZ u. So this determinant I should get, and if I equate to 0, then that is called a characteristic equation. What is this determinant? Is called a characteristic polynomial. So making this characteristic polynomial equating to 0 is what is called a characteristic equation. So if I work out for this determinant, see this a11 into a122 minus these terms, right? So if I do so, it's going to be s square plus, I will have now s coefficient. So s multiplied by this and s multiplied by this. So I would have that comes out to be C alpha F plus C alpha R by mu into s, and then here this product. So plus a squared C alpha F plus B squared C alpha R by IZZ u into S, right? And then I have these two terms, constant terms, multiplication. So that's going to be plus C alpha F plus C alpha R by mu into A squared C alpha F plus B squared C alpha R by IZZ u minus of these two. So this minus goes off. So I will have multiplication inside these terms. So that's going to be minus AC alpha F plus BC alpha R by mu again minus AC alpha F plus BC alpha R by IZZ u minus, in bracket, minus AC alpha F plus BC alpha R by IZZ u into u to u. That's equal to 0. So look at this this term. Third term is this diagonal product. So first this into this minus this into u. That's what is written. So now I can further reduce this and bring it to a convenient form. So I can have this details products of these terms, and then I'm going to further reduce. It's a good exercise. One can enjoy doing this. So what am I going to do? I'm going to multiply this. See, I have a denominator IZZM. So I'm going to multiply throughout by IZZM. Multiply with IZZM throughout this equation. So what is this going to be? It's going to become IZZM here into s square. And I would have inside this, see here m is there, so when I multiply m goes IZZ into this, and here m will be there, right? So when I do that, so I'll just write this expression. You can later on work out how does it come. So I z plus a squared into c alpha f plus I z plus b squared into c alpha r by u. This all are coefficient of s. So I was trying to get coefficient of s. So here I have coefficient of s, here I have. So I also multiply with the I z. So I would have my expression like this changed. Plus I would have here a squared c alpha f square by u square plus a squared c alpha f c alpha r by u square plus b squared c alpha f c alpha r by u square plus b squared c alpha r square by u square. Then I would have a term minus, I will have some similar term with the negative sign. So I would have this to cancel. So minus a squared c alpha f square by u square. So this get cancelled. I would have here a b c alpha f c alpha r by u square plus again a b c alpha f c alpha r by u square, and this term goes off. So b squared c alpha r square by u square, this goes off. This is all equal to 0. Right, any other term since any other term other than this, ma minus ma c alpha f plus md c alpha r, that's all equal to 0. Because I have this all, right? So I can again reduce this equation. So this equation can be, let's just look at this equation. This equation can be further reduced to mizz s square plus, I have this as it is. So izz plus a squared into c alpha f plus izz plus b squared into c alpha r by u into s plus, now you see here I have a squared this, b squared this term, and here ab, so this is 2ab. So you can see in all these terms c alpha f, product of this lateral stiffness is c alpha f and c alpha r by u squared is common. If I take that out, it's going to be a squared plus b squared plus 2ab. So what is that? It's a plus b whole square. So you know a squared plus b squared plus 2ab is a plus b whole square, where a plus b is L, so it's L square. So I would write now that as L square c alpha f c alpha r by u square. So these 1, 2, 3, 4 terms are reduced to the single, and plus here I take m out. So what is that I'll have is a b c alpha r, b c alpha r, b c alpha r minus a c alpha f, that's all equal to 0. So this is my characteristic polynomial. This is my characteristic polynomial. So again, you see there are two terms here. These two terms can be combined like this. How it will be combined like this? I would make one term as 1. So I will take this L squared C alpha F C alpha R by U squared out. Then I would have this same here, M I Z S squared plus this bracket into S plus I will have here 1 plus, so when I take L squared C alpha R by U squared out, which become 1, and here it will become in denominator, right? So this will be M into BC alpha R minus AC alpha F by L squared C alpha F C alpha R into U square. Into U square. That's equal to 0. That's equal to 0. When I take the term out, I should also have that outside, right? Just a minute. Yeah, when I take that out, I should also have that here. I forgot to put. So here I have taken L squared C alpha F C alpha R by U squared out. That's equal to 0. That's equal to 0. So here I can again rewrite this. Sorry, I have my mouse battery. I have to change. It's gone. So I undo. Extend this. Now, now this term, if you look at here, I can rewrite this term alone as 1 plus k3 u square. 1 plus k3 u square, where this k3 is what is called m into given with m into b c alpha r minus ac alpha f by L squared C alpha F C alpha R, called the stability factor. Right? There is a relationship between stability factor and understate gradient. This we will see later on. Right? So this is something as what is characteristic polynomial equating to 0, giving you characteristic equation, and in that characteristic equation you are expressing now this as a algebraic equation, right? So you have S, it's a quadratic equation. So S squared term, S term and the constant term, and equating this to 0, and I can get two roots, and then looking at the roots I would be able to see are they complex conjugate roots or real roots, or only or it is having real plus complex conjugate, no, it's a complex number root, no, all you can investigate that later on. So that is what is stability analysis. Later on that we will do. And now this equation, what we have derived is what we call it as fourth equation, is what is called a characteristic equation. Equation, and used for comparing different vehicle handling behavior. Right? So now, since you have this polynomial on left hand side, this polynomial is what is actually Si minus A, right? So now let us look at our equation number 3, what we had. Equation number 3 is what? Cx equal to that we had here, right? Cx equal to B into B, Cx equal to B. So this is what is a set of algebraic equation, where x is now your this. See, e raised to st vu is what is nothing but your q. That's what you are assuming here. You are assuming here. So you have your two variables v and r, and now c into this vector is equal to b is what are two algebraic set of algebraic equation. So if we have that, I can apply Cramer rules to get my steady state gain. So what do you mean by steady state gain is what we have seen. There are 5 steady state gain that we can have, that we put it in this previous slide. So here you could see. So these are essentially for the given steering input. So I have lateral velocity response means what? Lateral velocity response gain, let me call gain. So how that has been obtained? It is nothing but V for given steering input. So this as s tends to 0, whatever you have. So I can have V now as a polynomial, delta denominator I have V by delta as ratio of 2 polynomials. In that s tends to 0 when I put, I would have my steady state gain. Or simply it's function of s in numerator polynomial and denominator polynomial given, that's called a transfer function. So for the given input steering angle, what is my yaw velocity, lateral velocity? So that is my transfer function. So that is why you see this representation very quite useful representation for control system design, right? So this is what is now R by delta as s tends to 0, and lateral acceleration response is V dot by delta. So that is how do we write? You have to substitute that. So we have V dot. We have this, right? V dot plus Ru. So A is what is V dot plus Ru. So this is A by delta. So A is what is centripetal acceleration. So An by delta. So that would be actually V dot plus Ru by delta. So R by delta I have it here, and this V dot has become when I take in a Laplace form, this S V of S plus Ru by delta. So I would be able to have V by delta. This term sum is what is going to give me lateral acceleration response. What is curvature response? So curvature response is 1 by R is what is curvature, the turning radius by delta. So that is curvature response. And then you have another response. What is side slip response? So side slip response is beta by delta. Right, so these all are quite useful steady state gains, and these gains are used to compare the handling characteristic of different vehicles. So that is what we have to do, and that to do now we are going to look at this equation. What equation is this? C Q is what is equal to B. So this is in a algebraic set of algebraic equation. So that I get simply Si minus A. This is determinant, right? Into VR, that's equal to C alpha F by F. C alpha F by I is that AC alpha here into delta. So now what is my V by delta? So that's going to be, so this is my B matrix, right? So I will have ratio of determinants. That's what is, this is given by ratio of determinants. So denominator determinant delta is what is Si minus A. So in this, delta is what is Si minus A determinant. That would be in the denominator, and numerator determinant would be the first term. So out of this, V is the first variable. So Si minus A term, I should replace this first here. So I will have here B vector and the second column of Si minus A. In this denominator determinant, second term will be as it is, and I will have to replace the first term. So that's going to be as it is this. So if I have this matrix as A11, A12, A21, A22, and this is B1, 1 and B2 1 as this. Then what is that I would have here? I will have here A12 A22, right? So this is equal to B11 B21 A12 A22. So this determinant divided by Si minus K determinant. So here I have now characteristic polynomial. Here I will have one polynomial as function of S. So if you look at here, this order will be less than this or equal to this order. So here I have S squared term. So here I would have S first order algebraic equation. So this is my this is my response, steady state response, and in that if I put S tends to 0, I would have steady state gain. So similar way you can proceed for the remaining, and you would get the corresponding expressions, and those expressions are having many more interpretation physically from the variations, and that all we will see in the next class, right? Just you can work out, and we will again continue this, finding the steady state gains and then interpreting the steady state gain physically in our vehicle. And that is what is steady state response. Then we will go for finding out how can you go about finding transient response of your bicycle model, right? So that is all the upcoming class plan. And at this point, let me stop the lecture. If you have any doubts at this point of time, you can ask. Any doubts? Vineet Krishna is there? No doubts. Vaibhav? Abhinath? If there are no doubts, let me stop recording.